Welcome to the course Introduction to Electrical Engineering, and we will discuss today this lecture 5 on analysis of DC circuits part 3. Well, the outline of today's presentation will be the introduction, then voltage division in series circuit, current division in parallel circuit, Kirchhoff's laws, mesh analysis, super mesh concept, node analysis, super node concept, and then we will talk some exercises as a preliminary exercise, then followed by some of the numerical solved and unsolved problem, followed by the references like. So, coming to the introduction for this, the currents, this current get divided into different paths when the resistances are connected in parallel. Hence, the current division is applicable in parallel circuit. Well, voltage get divided into series, but the current remain the same. Hence, the voltage division is applicable in series circuit only. The current and voltage follow Kirchhoff's current law, in short we call it KCL, and the KVL, Kirchhoff's voltage law in the circuit at junction point, nodes and in loop. Of course, Kirchhoff's current law used at node and Kirchhoff's voltage law used in loops. More than one loop forms mesh of electrical circuit and requires suitable analysis to solve such complex circuit. Current and voltage division finds application in manufacturing of electrical meters and sensor devices, as you can see here the typically the DC voltmeter as well as the sensors, Hall effect sensor as well as the typically the ammeter with of course, the multimeter here. The voltage division is also used in reducing the voltage level to lower value using the voltage divider and 200 kilovolt voltage divider with the ratio of 10,000 to 1. Then the voltage division concept is also used making a rheostat and potentiometer. Here typically you can see potentiometer and then the rheostat here. You can take part of the resistance as a output from this, giving the input to this, and you might have seen the rheostat also in the laboratory we use for this purpose for dividing the voltage like on. Then the voltage division concept is also used in making radios, amplifier and electronics devices for adjusting signal level in electronics devices like your radios and amplifiers and then the printed circuit boards of these circuits. Well, the resistance voltage dividers are used for measurement for full and front chopped lighting impulses or impulse voltage, as you can see in the diagrams like resistive voltage divider. Then the 600 kilovolt high voltage capacitive voltage divider, you can see in the diagram with the typically with the different components of it of this voltage divider. The principle of voltage division and current division is used in potential transformers and current transformers for stepping down high voltage and high current into the power plant for the purpose of measurement or for the purpose of sensing the large voltage and large current like. Well, Kirchhoff's laws are used to help us to understand how the current and voltage work with the within the electrical circuits. The mesh analysis and node analysis help us to solve the complex electrical network. You can see how looks like a complex electrical network here of the wiring. Then coming to the of voltage division. So, the total voltage gets divided into series circuit and current remains the same. The voltage division rule can be understood by considering a series circuit shown here. As you can see, the current is the same in the entire network consisting the voltage source and two resistances connected in series. The voltage is divided between across the two resistance and current is the same in entire network. So, they are connected all three elements in series like. So, we can apply the Ohm's law. So, R equivalent will be V upon I, and we also know R equivalent is a series resistance of this circuit given as R equivalent to R 1 plus R 2, and putting the second relation into 1, you can find out the current like I equal to V upon R 1 plus R 2 as it is shown in the figure like. So, now we can find out the voltage across these series resistor. V 1 will be equal to I into R 1 and V 2 will be I equal to R 2, and putting the like typically the 3 into 4 the relation and voltage drop across R 1 can be find out V 1 equal to R 1 divided by R 1 plus R 2 into V. Virtually V upon R 1 plus R 2 is the current, multiply the resistance R 1, that gives the V 1. Similarly, putting the value 3 into 5, the voltage drop across R 2 can be calculated. V 2 equal to R 2 divided by R 1 plus R 2 into V. Of course, here the V divided by R 1 plus R 2 is the current, multiply the R 2, that is the voltage across the R 2. Well, the V divided among the resistance in direct proportion to their resistances, and larger the resistance, large will be the voltage drop across it, and this called the principle of voltage division. For n resistors in series, the voltage across the resistance is given at V n equal to R n into V divided by all the resistances R 1, sum of all resistances R 1 plus R 2 plus R 3 plus up to plus R n, like. So, the different types of voltage division circuits are, as you can see, the two resistances are connected here. The input voltage given to across the total resistance, and output is taken only V out across the R 2, and similarly the voltage input is shown here as a equivalent to this of A, and in the B network you can find out the again in different way to putting input voltage and output voltage with this network shown in these three circuits, in two circuits of A and B. Now, coming to the, that was for voltage division. Now, coming to the relations for current division. The current division, total current gets divided into parallel circuit and voltage remains the same. So, current division rule can be understood by considering a parallel circuit shown here. So, you have a voltage source and have connected across the two resistance in parallel, and it has a two node A and B, on which the two resistance, these two resistances are connected, and of course, current drawn from the source is I, but the current flowing into these two resistances is I 1 and I 2 going through R 1 and R 2. Well, here applying the Ohm's law, we can find out V equal to I into R eq, where R eq is the equivalent resistance of both resistances in parallel, and the branch currents here I 1, I 2. So, we can find out the, of course, the now current I 1 equal to V 1 upon R 1, because this voltage source is directly connected across both the resistance. So, current flowing into the R is directly V 1 V upon R 1, and I 2 is equal to V upon R 2, like. So, now from branch currents are known. So, we can find out like a typically I 1 equal to I into R eq upon R 1, and I 2 will be I eq into R 2, where I R q is a typically the voltage across it divided by the resistance will be the current through it. So, also we know in parallel circuit R equivalent to R 1 into R 2 divided by R 1 plus R 2 of this resistance network. Well, so we can find out the value from putting that relation from 13 to 11 and 12. So, I will be, you can call it, I will be equal to R 1 R 2 into R 1 into plus R 2 divided by total R 1. So, that is virtually you can call it the equal to voltage divided by R 1. Similarly, you can call it final relation, we can call it like this will be I R 2 by R 1 plus R 2, and we can find out I 2 similarly I into R 1 R 2 divided by R 1 plus R 2 divided by R 2. So, that is we can find out how it is R 1 and R 2 you can find out equivalent to that. Well, so moreover this I 2 is equal to I R typically R 1 divided by R 1 plus R 2, because I R is the voltage across, and then you can find out R. So, the total current is shared by the resistors in inversely proportional to their resistances, and this is known as the principle of current division. And in terms of conductance, we can find out I 1 equal to I G 1 divided by G 1 plus D 2, and I 2 equal to I G 2 divided by G 1 plus G 2. So, now coming to the duality between series and parallel connect circuits. Duality between series and parallel circuit is there is a certain peculiar pattern of relationship between series and parallel circuit. On comparing series and parallel circuit, voltage takes the place of current and current takes place of voltage, and this pattern called the duality. Well, two circuits having duality pattern are said to be duals of each other, and here is the duality between series and parallel circuit. The voltage, current and resistance in a series circuit have a corresponding dual counterpart in terms of current, voltage and conductance of a parallel circuit. So, if we talk about series circuit having two different resistances, so the current in series circuit is the same. It means the current flowing all the elements will be I 1 equal to I 2 equal to I 3, all currents are same, but the voltage total voltage divided across all the resistances. So, is V 1 plus V 2 plus V 3 up to V n, and resistance also directly get added R t equal to R 1 plus R 2 plus R 3, and current will be your same. So, V 1 upon R 1 or V 2 upon R 2, V 3 upon R 3, and voltage across of course, V 1 will be V 2 into V t divided by R t, that is the current multiply R 1, V 2 equal to V t upon divided by R t into R 2. So, that is the voltage across different element in series circuit. Now, coming to parallel circuit, the voltage across all the elements are equal corresponding to duality. I mean V 1 equal to V 2 equal to V 3 up to maybe V n, and total current is the sum of all the current of all elements, I t equal to I 1 plus I 2 plus I 3 plus, and G t will be conductance here will be the sum of all G 1 plus G 2 plus G 3, and your voltage will be I 1 upon G 1 equal to I 2 upon G 2 equal to I 3 upon G 2, because voltage is same across all elements, and current I 1 will be I t into G 1 upon G t, and I 2 equal to will be I t upon G t. I t upon G t is virtually the voltage, and multiplied V 2 G 2 will be the current corresponding to that. So, this is the concept of duality in series and parallel circuit like. So, coming to network analysis. So, defining the current in each branch, voltage at each node and power flow through each element is under network analysis, and there are two approaches to network analysis: a direct method, indirect method. Coming to the direct method, in direct method network is left in original form while determining the element voltages and currents, and used for simple circuit. Example is Kirchhoff's law, loop analysis, nodal analysis and superposition theorem, etc. In indirect method, the original network is converted into a much simpler equivalent circuit for rapid calculation of different quantity and applied to simple as well as the complicated network. Examples are delta to star to delta convergence and Thevenin theorems and Norton theorem. Coming to Kirchhoff's law, we of course, Kirchhoff's laws are the two equality that deal with the current and voltage in electrical circuit, and they were first described in 1845 by German physicist Gustav Kirchhoff. You can see the typically photograph of the inventor, and Ohm's law by itself is not sufficient to analyze the circuit. That is why the Kirchhoff's law is devised. So, when it is coupled with the Kirchhoff's law, we have a sufficient powerful set of tools for analyzing a large variety of electrical circuit, and Kirchhoff's current law is based on the law of conservation of charge, and Kirchhoff's voltage law is based on the law of conservation of energy. Kirchhoff's laws can be applied to AC circuits in the same way as for DC circuit, provided we use phasor sum rather than their algebraic sum in AC network. Coming to Kirchhoff's current law, in short is called KCL as a Kirchhoff's current law. So, Kirchhoff's current law can be stated as Kirchhoff's current law states that the algebraic sum of current entering a node or a closed boundary is 0. So, figure shown here shows the current are entering into and leaving to a node A. I mean like, so sum of all these currents will be equal to 0. So, you can call it before applying KCL, sign convention is very important. So, following sign convention may be used. So, current entering we can take negative, current leaving we can take positive because of arrow. So, applying the Kirchhoff's current law with the sign convention, we can say because I 1 is entering. So, we are saying it is with the minus sign. So, minus I 1 plus I 2 is leaving, minus I 3 current is entering, minus I 4 current is entering, and plus I 5 that current is leaving equal to 0. So, sum of all currents are 0 here, and from we can rearrange here. So, I mean here comes all the entering current will be equal to all the currents leaving current. So, I 1, I 2, I 4 are entering. So, it will be I 1 plus I 2, I 3 plus I 4 will be equal to current leaving, that is I 2 plus I 5. So, alternately Kirchhoff's current law is also stated as the sum of the current entering a node is equal to the sum of the current leaving the node. Now, coming to the Kirchhoff's voltage law, in short it is also called KVL. So, Kirchhoff's voltage law states that the algebraic sum of all the voltage around a closed path or loop is 0. To illustrate KVL, consider the circuit shown here with the voltage source V s and you have a resistance R2 and R1 R2 connected to in this network. So, we can say assign the current direction in the loop clockwise or anti-clockwise first, then write the KVL equation by moving in closed loop which has a resistances and sources, and voltage drop across the resistance is taken as a positive path is travel the same direction as that of current in step 1. The voltage drop across the resistance is taken as a negative if path is travel in opposite direction as that of current in step 1, and polarity of voltage source in KVL equation depends on the voltage polarity which comes first either plus or minus while moving the path. And you can see here as a step 1, let us assume the clockwise current direction in the loop of this where source voltage Vs, and you have a X node with the R1 R2 resistance, and it has in the loop current I. So, step 2, moving the direction of current and writing KVL equation. Let us assume we start moving from location X towards the right, then for the resistance R1 drop will be positive as we are moving towards right in the direction of current, and similarly for R2. And step 4, after R2 we reach the voltage source and at negative polarity comes first. So, we write it as a minus Vs, and hence the overall KVL equation becomes your I R1 plus I R2 minus Vs equal to 0, and moving towards left from the X, KVL equation remains the same. So, you can write V S minus I R2 minus I R1 equal to 0, that does not change, like you can move in right direction. So, rearranging term you can call it like a V s equal to I R1 plus I R2, and if the voltage drop across resistances are termed as a V 1 V 2, you can write V s equal to V 1 plus V 2, and furthermore you can write V s as a total equation of previous one, V s minus V 1 minus V 2 equal to 0. So, this equation says that total voltage, the sum of drops across each resistance is equal, which is known as Kirchhoff's voltage law. To avoid the violation of KCL or Kirchhoff's current law, two current sources in series cannot never have a different current. So, in series current remains the same, as you can see the different voltage source, but current through this is the same. Voltage can be added because they are connected in series. So, this is equivalent of that. To avoid the violation of KVL, two voltage source connected in parallel will always have a same voltage. So, they cannot have different voltages in parallel. So, in parallel circuit voltage remains the same, as you can see the three current sources. So, voltage here all will be equal to same, but you can add the current all currents here like. So, mathematically KCL is written as means your n equal to 1 to n as a I n equal to 0. So, it means sum of the all currents equal to 0 at a node, where n is the number of branches and I n is the nth branch current entering or leaving the node. Then similarly, for KVL, for voltage across the total m elements, mathematically in KVL it is written as small m equal to 1 to capital M and V m equal to 0, where this your in the circuit is shown what is your sum V 1, V 2 and V n like. So, coming to like a mesh analysis. So, loop, it is a closed path with no node passed more than once, and mesh, a mesh is the loop that does not contain any other loop within it. Well, mesh analysis is only applicable to circuit that a planar circuit, and planar circuit is known as a planar circuit is one that can be drawn in a plane with no branches crossing one to another, and non-planar circuit, a non-planar circuit is one that can be drawn in a plane with branches crossing one to another, and some of the circuit may have crossing branches, but they can be redrawn as a planar like. So, you can just see here this circuit is a planar circuit, like look like complicated circuit, but you can see when it is written equivalent here, shown equivalent to here, no branches crossing each other, that is why it is a planar circuit, and here you can see the non-planar circuit because branches are crossing each other like. So, let us learn the mesh analysis to planar circuit that do not contain the current sources, and in the mesh analysis of circuit with n meshes, we take the following three steps. Assign the mesh current I 1 I 2 in the n meshes and apply KVL to each of the n meshes, use Ohm's law to express the voltage in terms of the mesh current, and solve the resulting n simultaneous equation to get the mesh current. So, consider the circuit shown here with two meshes, currents are assigned in clockwise direction in each mesh, and let us analyze the mesh for calculation of current using the Kirchhoff's voltage law in each mesh. So, all the currents and voltage are shown here, like you can write the in this circuit now the equation of KVL in mesh 1. So, it is minus V 1 plus R 1 I 1 plus R 3 that is the equation for mesh 1, and apply the KCL at node B, that is minus I 1 that is current entering, and plus I 2 plus I 3 that the two current are leaving. So, you can from this you can find out the relation equal to I 3 equal to I 1 minus I 2, and substituting this this equation into earlier equation. So, it comes like V 1 equal to R 1 plus R 3 into I 1 minus R 3 I 2. Then applying the Kirchhoff's voltage law in mesh 2. So, mesh 2 we start from typically from B node. So, it will be R I 2 plus V 2 minus R 3 and replacing I 3 we can have R 2 I 2 plus R V 2 minus R 3 in bracket I 1 minus R 2 equal to 0, and substituting the relation from this. So, we get a V 2 equal to minus R 3 I 1 plus R 1 plus R 2 into I 2. Now, these two equation of mesh 1 and 2, I mean these can be solved for to obtain the two unknown I 1 and I 2. Moreover, I 3 can also be obtained, which is difference of the two, and hence the two mesh circuit currents are calculated when voltage sources and resistances values are given using steps of mesh analysis. So, in case of three meshes in a circuit, there are three equations. So, we use Cramer rule to solve the three linear equation. So, here typically you can just see, I mean let us learn the mesh analysis to planar circuit that contains the current sources. So, two cases assigned here, and you can just see typically how the here the case 1 current source exists in arm of A of mesh typically in this mesh 2, and the current source exists in between the meshes. So, these are two examples where the current sources are shown here along with the voltage source and resistances like. So, taking an example of case 1, calculate the makes the calculation easier as a current source itself, your value of current flowing in that mesh. So, you directly know the current in the second mesh, hence the I 2 becomes minus I 5 because it is a opposite current than what is shown as a symbolic in I 2. Putting the value of I 2 in KVL, current in mesh 1 easily calculated. So, and from this you can find out easily the value of I 1 like your one is known another. Now, coming a concept of super mesh concept. So, when current source dependent or independent occurs between the two meshes, we apply super mesh concept to solve the circuit, and we create a super mesh by excluding the current source and any elements connected in series with the while applying the Kirchhoff's voltage law. Let us solve the such circuit shown here on this typical example, that circuit second circuit shown here, and converting this figure having two meshes into a circuit having a single super mesh. So, that is single super mesh shown in the right side like by leaving this just the current source here, and from which we can find out typically applying the Kirchhoff's voltage law to mesh super mesh. So, this minus 20 plus 6 I 1 and that is plus 10 I 2 plus 4 I 2 equal to 0, that is the outer mesh you can call it. So, we apply 6 I 1 that give you like a 6 I 1 plus 14 I 2 equal to 20, and applying the KCL at the bottom node we can find out I 2 equal to I 1 plus 6 from this circuit like on the bottom node like. So, we can easily solve above two equations to obtain I 1 and I 2, and a super mesh requires the application of both KVL and KCL like. So, coming to now node analysis. What is the node analysis? The node analysis is the method that provides the general procedure for analyzing the circuit using the node voltage as the circuit variable, and also called node voltage method. Type of nodes in node analysis is the non-reference node, the node voltage which has a definite node voltage, and reference node, it is the node which acts as a reference point to all the other nodes, also called datum nodes. As you see here, the 0 is the datum node and 1 2 is the your non-reference node. So, 0 node 0 is the reference node and nodes 1 2 are your non-reference nodes like. And now reference node indication, I mean by ABC. So, common symbols for indicating reference nodes as a common ground, then ground and chassis ground, and chassis ground, that is the C, used in devices where the case enclosure or chassis act as a reference point for all the circuit, and earth ground used when the potential of earth is used as a reference. Like now, steps to find out the node voltage: select the node as a reference ground node and assign voltage V 1, V 2 n minus 1 to the remaining n minus 1 nodes, and apply the Kirchhoff's current law to each node of n minus 1 non reference node, because one node is your reference node, that is ground node, and then use the Ohm's law to express the branch currents in terms of the node voltage. Solve the resulting n minus 1 simultaneous equation to obtain the unknown node voltage, and for n nodes there will be n minus 1 simultaneous equations to be solved to get all the node voltage. The examples here depicting the nodes as we show here. So, we have here, you can call it like a typically the circuit shown here, I mean with the different nodes, like you have a node 1 to 0. So, 0 is your reference node or bottom node, and here it is 1 and 2 in the previous circuit, and second circuit is 3 nodes like 1, 2, 3. So, you have a 4 nodes where 1 is non-reference node and 2 here is the non-reference node and 3 are the non-reference node. So, it is a dual of the mesh analysis, involve the application of KCL, Kirchhoff's equation instead of KVL, and one of the nodes is taken as a reference or bottom node with the maximum number of branches connected to preferred, and the reference node is assumed to be a ground or 0 potential, and potential of all other nodes are defined with respect to reference node, and KCL equations, Kirchhoff's current law equations are written for each node except for the reference node. On solving, node voltage are obtained. Now, there is again the concept of like a super node concept. Here we call it the definition of super node is when a dependent or independent voltage source is connected between the two non-reference nodes, then these nodes form a generalized node which is known as a super node. And you can see here the node 2 and 3, they are typically the super node. Node 2, 3 are super node because a voltage source of 5 volt is connected between these two nodes. So, super nodes can be regarded as a surface enclosing the voltage source at two nodes. So, while nodal analysis is better choice compared to the mesh analysis, so nodal analysis can be applied for both planar and non-planar circuit, but the mesh analysis can be applied only to planar circuit. So, where the planar circuit is a circuit that can be drawn on a plane with no cross wires, and the choice between node voltage analysis and mesh current analysis is unambiguous, and to choose between the methods, pick up the one that involves solving the fewest equation or less number of equations like. So, why the node analysis is better than choice compared to mesh analysis? So, another reason is the number of voltage variables, and hence the simultaneous equation to solve equal to the number of nodes minus 1, because one node is or your reference node or ground node. So, every voltage source connected between the reference node reduces to number of unknown and equation by 1, and node analysis is thus best for voltage sources. So, number of current variables, and hence the simultaneous equation to solve equal to the number of meshes, and every current source is a mesh reduces to the number of unknown by 1, and mesh analysis is thus best of the current sources. So, mesh analysis however cannot be used for network which cannot be drawn as a planar network, that is why with the no crossing component. So, since the nodal analysis require a smaller number of equations to be solved, one can consider it as a better choice as compared to the mesh analysis. So, for the circuit having n number of nodes and loops, nodal analysis require only n minus equations, while mesh analysis require n equations to be solved. Now, coming to typically some of your problems. So, as a kind of short problem where current division problem arises in parallel circuit, and in which type circuit KVL and KCL are not applicable, it is a distributed parameter circuit where parameter is changing. The KVL and KCL are based on which law of conservation? The Kirchhoff's voltage law is based on conservation of energy, and Kirchhoff's current law is based on conservation of charge. Question 4, what is the KVL and KCL? KCL is the sum of the currents entering is a node equal to the sum of the currents leaving the node, and KVL is Kirchhoff's voltage law states that the algebraic sum of all the voltage around a loop closed path or loop is the 0. Like, if the KCL or KVL are applicable for both DC AC circuit, answer is yes, you can apply KCL and KVL both AC as well as DC circuit. On which law the mesh analysis is based? Mesh analysis is based on the Kirchhoff's voltage law. The node analysis of circuit mainly based on which law? Kirchhoff's current law and Ohm's law. For the network of n nodes, the number of simultaneous equation is to be solved is n minus 1, because one node is your reference node or ground node. What is the concept of super node used in instead of node analysis? And the network has voltage source between the two nodes, these two nodes are called super nodes. When is the concept of super mesh used in instead of mesh node analysis? When the network has current source between the two meshes. Now, coming to some of the solved numerical problems. To calculate the voltage, different voltages that can be obtained from 25 volt source across the different terminals, like starting from DCBA. So, here we can calculate the total circuit resistance R1 plus R2 plus R3, I mean that is keeping value it will be 12.5 kilo ohm, and voltage across R1 will be using the voltage division. I mean your V1 will be equal to the Vs upon RT, that is the current in the circuit multiplied R1, and that will be 1 upon 12.5, we got it into 25, that is a 2 volt, and voltage at the point B will be your Vb, Vs minus V1. So, that will be 25 minus 2, 23 volt. Similarly, V2, the voltage across the resistance R2 will be your Vs upon RT, that is the current into R2. So, 8.2 divided by 12.5 into 25, that is 16.4 volt, and voltage at point C will be your Vb minus V2. So, that is your 23 minus 16.4, 6.6 volt. Similarly, voltage across R3 is given your Vs upon RT, current multiplied R3, that is 3.3 divided by 12.5 into 25, that is 6.6 volt. So, that is first problem. Now, coming to problem number 2, a 10 ohm potentiometer connected in series circuit as an adjustable voltage divider. So, what is the range of voltage V1 can be obtained by adjusting the potentiometer through its entire range. So, we have a source of 24 volt and we have a 3 resistance 5 ohm, 10 ohm and 10 ohm, and there is a 10 volt potentiometer here, which we can vary the voltage output voltage across it by moving this pointer. To find out the total circuit resistance, that is RT equal to R1 plus R2 plus R3, that is 5 kilo ohm, 10 kilo ohm plus 10 kilo ohm equal to typically 25 kilo ohm. I mean correction here, typically the total voltage E appears across the end of terminal potential. So, Vp will be R2 upon RT into Vs, and that is 10 upon 25 into 24, 9.6 volt, and the Viper arm is at the top of the potentiometer. V1 will be 10 upon 10 into 9.6 volt, and when Viper is at the bottom of the potentiometer, it will be 0 volt, because 0 upon 10 into 9.6, that is 0 volt, and when Viper is in arm is in the middle. So, it will be your 5 upon 10 into 9.6, that is 4.8 volt. So, hence the voltage divider helps to obtain the different voltage from the fixed input voltage of 24 volt. Now, coming to the question 3, find the branch currents using the current divider rule for a parallel conductances as shown here in figure. So, you have 3 conductance 0.5 Siemens, 0.3 Siemens and 0.2 Siemens G1, G2, G3, and drawing the current I1, I2, I3 form a current source of 4 ampere total current like. So, now we can find out the total conductance of this circuit Gt equal to G1 plus G2 plus G3, that comes 1 Siemens, and now I1 we can find out I upon Gp will be the voltage across it divided by multiply G1. So, it is 0.5 divided by 1 into 4, that is a 2 ampere. Similarly, I2 will be G2 upon Gp into I. So, 0.3 divided by 1 into 4, that is 1.2 ohm ampere, and I3 will be your G3 upon Gp into I, that is 0.2 divided by 1 into 4, that is 0.8 ampere. Find the 3 branches currents in the circuit shown in the figure shown here. What will be the potential difference between the point A and B in this circuit? So, you have 2 current sources which are working in opposite direction, and you have 3 conductance, I mean having 3 current I1, I2, I3. So, we can convert equivalent to a circuit of single current source because these two current sources are working in opposite direction. So, current sources in parallel add algebraically, therefore, the two current sources can be combined to give a resultant current source of a I equal to 24 minus 5 equal to 19 ampere. It is shown between A and B, and total circuit conductance will be sum of all three, G1, G2, G3, Gp will be equal to 0.95 Siemens, and applying current division rule. So, I1 can be G1 upon Gp, that is your into I into 0.5 divided by 0.95 into 19, that is 10 ampere. Similarly, I2 will be G2 upon Gp into I, that will 0.25 divided by 0.95 into 19, that is 5 ampere, and I3 will be G3 upon Gp into I, so that is 0.2 divided by 0.95 into 19, 4 ampere. So, as all the branches are in parallel, the voltage across each branch will be the same. So, VAB will be equal to I1 upon G1 equal to I2 upon G2, I3 G3, and that will be VAB will be a 10 divided by 0.5, 5 divided by 0.25 or 4 divided by 0.2, that is 20 volt. Now, coming to question 5, find the current I0 and V0 in the circuit shown here, where you have a one current source, one dependent current source of this I with the 4 ohm resistance, like a quite interesting problem. So, here in this applying the Kirchhoff's current law at node A, that is the current, two currents are entering, 3 ampere is minus 3 and 0.5 dependent current source is also entering 0.5 I, and the current leaving is plus I0 equal to 0. From this you can find out I0 equal to 3 plus 0.5 I0, or I will be equal to your 3 upon 0.5, that is 6 ampere. And for the 4 ohm resistor, Ohm's law now give V0 equal to I0 into 4 into I0, and I0 we got 4 ampere. So, 4 ampere, so 6 ampere. So, we know V0 equal to 4 into 6, that is 24 volt. Now, question 6, find the current I1, I2, I3 in this network, where the 12 volt source is there, and A node have a 5 volt, and we have a resistance R1 equal to 1 kilo ohm, R3 equal to 1.5 kilo ohm, and R2 equal to 2 kilo ohm. And typically current are having in all three branches I1, I2 and I3, and rest of the circuit is of course not known. So, using the Ohm's law, obtaining at getting I1 will be your voltage is here source is 12 volt minus Y1 node A. So, that will be divided by 1 kilo ohm, 7 milliampere, and I3, I mean that is the current going through it between 5 volt and 0 node, I mean that is reference node, minus 0 divided by 1.5, that is 3.33 milliampere. To obtain I2, we can have the same procedure as voltage of rest of the circuit is not applicable, hence the applying KCL at the I minus I1, that is current entering, and 2 current plus I2 plus I3 they are leaving. So, I2 will be I1 minus I2, that will be 3.67 ohm, and from this milliampere now we can multiply with the 2 kilo ohm resistance. So, we can find out the voltage at the input across the network. So, that will be 2 into 3.67, I mean like that is the voltage across the rest of the network you can find out. Now, coming to the question 7, find the value of I current and power dissipated by the resistor, where we have a 3 voltage source. I mean you can just see 2 are showing the polarity positive, but this is minus 8 volt like on. So, now coming applying the Kirchhoff's voltage law in this loop. So, minus 8, because it is minus is written here in bracket minus 8 plus minus 12, because current is living in the negative terminal, plus 10, that is a positive voltage. So, current is entering to positive, and plus 3 I, the drop in the resistance, and from which you can just get the value 6 plus 3 I equal to 0 and I equal to minus 2 ampere, means current is flowing in the positive direction. It means the current is moving in a positive direction instead of assumed convention, and power dissipated across resistance I square R. So, that will be 2 square into R 3, so to 4 into 3, that is a 12 watt. Now, coming to the question 8, find I1, I2 and I3 and V1, V2, V3 in the circuit shown. So, here we have a 30 volt source and we have 3 resistance 8 ohm, 3 ohm and 6 ohm. We have a node, and A node we have all 3 currents, I mean one is I1 is entering, I2, I3 is leaving, are leaving. So, assign the loop currents, direction of applying KVL in both loops, and applying the Kirchhoff's voltage law in first loop. So, minus 30, your current is entering with the minus polarity of the voltage source, plus 8 I1, that is the drop across 8 ohm, plus 3 I2, I mean current is going in this resistance is I2, that equal to 0. Now, second loop, I mean we can have like a 6 I3 minus 3 I 2. So, that is I 3 you can, where the I 3 from the Kirchhoff's current law at the node A will be equal to I 1 minus I 2. So, substituting this I 3 and solving this, we can get I 1 equal to 3 ampere, I 2 equal to 2 ampere, I 3 equal to 1 ampere. And applying Ohm's law, we can get typically from these current now, I mean like V 1 equal to your R 1 into I 1, that is 8 ohm into 3 ampere, that is 24 would be equal to I 2 into R 2, that is 3 into 2 ampere, that is a 6 volt, and I 3 R 3, that is your 1 ampere and 6 ohm, that is V 3 will be 6 volt. So, coming to question number 9, find the mesh current I 1, I 2 and I 3 using the mesh analysis. So, here again we have 3 currents and we have 2 voltage sources with the 4 resistance in this network. So, we can find out applying the first KVL in the first mesh. So, it is a minus 15 is the voltage source, current is entering with the minus polarity, plus 5 I 1, that is the drop, and plus 10 I 1 minus I 2, the current flowing into the 10 ohm resistance, plus 10 volt, and from this you can find out typically it will be 3 I 1, from this will minus 2 I 2 will be equal to 1, and applying Kirchhoff's voltage mesh 2. So, it will be your 6 I 2, the current flowing into I 2 into second, plus 4 I 2 plus 10 I 2 minus I 1, the reverse of previous one, minus 10, that will be I 1 minus I 2 equal to minus 1, and solving these two equation, of course, you can find out I 1 equal to 1 ampere and I 2 equal to 1 again 1 ampere, and I 3 will be I 1 minus I 2, that is your 0 ampere. So, you will have a typically 0 ampere in the this center branch. So, another you can use the mesh second method using Cramer law. The equation 28 can be solved also by using Cramer rule in matrix form. So, that is the relation from two equation we got this matrix 3 minus 2 minus 1 2 I 1 I 2 equal to 1 1, and calculating the denominator of it with the elements it is 4 and delta 1 equal to again 4, and from this delta 2 also this, and you can find out I 1 delta 1 total delta and I 2 equal to 2 upon delta, that is 1 1, and I 3 again 0. So, both the method can be applied, and network is smaller or simpler one. Coming to the question 10, find the mesh current I 1, I 2, I 3 and I 0 using the mesh analysis. I mean here you can have a 3 mesh, typically one dependent voltage source, another voltage source, and the typically different current with 3 resistors. So, applying the Kirchhoff voltage law is mesh 1. So, it is minus 24 because current is entering with the minus polarity of the 24 volt source, plus 10 I 1 minus I 2, that is the current flowing into the 10 ohm resistance, plus 12 I 1 minus I 3. So, it give you 11 I 1 minus 5 I 2 minus 6 I 3 equal to 12. Apply Kirchhoff's current law in the voltage law in loop mesh 2. So, 24 I 2 plus 4 I 2 minus I 1 I 3 plus 10 I 2 minus I 1 equal to 0. So, you get a relation minus 5 I 1 plus 19 I 2 minus 2 I 3, and applying the KVL in mesh 3, that is 4 I 0 plus 12 because that is a voltage source, plus 12 I 3 minus 7 plus 4 I 3, typically your in this case I 3 minus I 2, that is equal to 0. So, but at node 1 you can find out that I 1 I 0 equal to I 1 minus I 2, I 1 is entering and I 2 I 0 leaving. So, you can keep the value in terms of that. So, that comes like 4 I 1 minus I 2 plus 12 I 2 I 3 minus I 1 plus 4 I minus I 3, that give you relation I 1 minus I 2 plus I 2 I 3 equal to 0. Now, using Cramer rule for 3 unknown variables for I 1 I 2 I 3, you can have a matrix form with this relation, and you can find out typically different determinant your total determinant delta, delta 1, delta 2, delta 3, and from this you can find out the I 1 delta 1 upon delta 2.25 and I 2 equal to delta 2 upon delta 0.75 ampere and I 3 delta 3 upon delta 1.5 ampere. Find the mesh current I 1, I 2, I 3 and I 4 using mesh analysis in this network, and typically the mesh 1 and 2 form a super mesh because they are having a independent current source in common, and mesh 2 and 3 form another super mesh because they have a dependent current source. The two super meshes intersect and form the larger super mesh as shown. Applying the Kirchhoff's applying KVL in the large super mesh as shown is here. So, it is 2 I 1 plus 4 I 3 typically here and plus 8 I 2 minus I 3 minus I 4 plus 6 I 2. So, that is about one equation of this super mesh. Then we have the simplification I 1 plus 3 I 2 plus 6 I 3 plus minus I 4 applying Kirchhoff's current law at mode P here. So, that is I 2 equal to, that is the current entering, equal to I 1 plus 5, these two current are leaving, and applying the Kirchhoff's at node Q typically here. So, that is typically I 2 here equal to I 3, that is a current entering plus I 3 I 0, and but here I 0 equal to minus I 4. So, you can find out I 2 to I 3 minus 3 I 4 and apply Kirchhoff's voltage law in mesh 4 typically here. So, 2 I 4 plus 8 I 4 minus I 2 plus 10 equal to 0 in this. So, solving this equation, so you will get I 1 equal to minus 7.5, I 2 equal to minus 2.5, I 3 equal to 3.93 and I 4 2.143. Coming to question number 12, calculate the node voltage in the given circuit. So, there are 3 nodes V 1, V 2, typically 1, 2 and 0 reference node and 1, 2 are non-reference node. So, each one node voltage V 1, V 2 are assigned and also the direction of branches current are marked with respect to the reference. So, applying the Kirchhoff's current law at node 1 and 2 here. So, you can find out from typically node 1, that is I 1 current is ending equal to I 2 plus I 3 and node 2 I 2 plus I 4 here equal to I 1 plus I 5. So, applying Ohm's law at KCL equation. So, Ohm's law to KCL equation node 1, you can find I 1 equal to I 2 plus I 3 equal to typically 5 equal to V 1 minus V 2, these two node divide by 4 plus V 1, that is here divide by 2 this relation. So, that gives the relation 3 V 1 minus V 2 equal to 20 ampere. Similarly, you can have Ohm's law on Kirchhoff's current law is node 2, that is I 2 plus I 4, that is the current 2 sources equal to I 1 plus I 5. So, that is typically the current typically coming here in 4 ohm V 1 minus V 2 upon 4 plus 10, that is 5 plus V 2 minus I 6. So, you get another relation 3 V 1 plus 5 V 2 equal to 60, and solving these two equation of V 1 V 2 you get V 1 13.33 and V 2 equal to 20 volt. Calculate the node voltage in the given circuit of node V 1. So, there are 2 nodes, node 0 reference node and node 1 is the non-reference node. So, node voltage is assigned V 1 and also direction of branch current are marked with respect to reference node. So, applying the Kirchhoff's current law at node 1. So, you have I 1 plus I 2 plus I 3 equal to, because all 3 currents are leaving, equal to 0. So, applying Ohm's law to Kirchhoff's law, you can have V 1 upon minus by 12, that is the current, let us say I 1 plus V 1 minus V 60, that is divided by 7, that is 4 I 2, and third V 1 minus 0 by 4 is equal to 0. So, you get the, from solving this V 1 equal to 18 volt. Now, from V 1 we can find out the branch current. Once you know V 1, that is V 1 minus 0 equal to 12. So, 12 by 12, 18 by 12, that is it 1.5 ampere, A 2 V 1 minus 60 upon 7. So, from this minus 6 ampere and I 1 V 1 upon that is 18 by 4, 4.5 ampere. So, coming to question 14, calculate the node voltage in the given circuit containing the super node, because this is the voltage source here between V 2, V 1, V 2. So, they become super node. So, hence the 2 voltage source is connected between node 1 and node 2, hence it forms super node with 12 ohm resistance in parallel. So, V 2 minus V 1 equal to 2, always whatever may be the value of resistor. So, the 10 ohm can be removed and the circuit can be redone and applying the KCL to super node. So, we can just remove that and it becomes the, you can call it the circuit now. So, expressing in terms of the nodes. So, your 2 volt equal to V 1 upon typically 2, that is typically the current goer, V 2 minus typically your 0 by 4 plus 7. So, that comes as one equation 8 equal to 2 V 1 plus V 2 plus 28 and V 2 equal to minus 2 1 minus 20, and you have a V 1 plus 2 minus by 2 V 2 equal to V 1 plus 2 from this circuit, and from which you can solve it. So, V 1 comes minus 7.33 and V 2 comes minus 5.33 volt like. Question 15, calculate the node voltages in the given circuit. You have 2 nodes and there are 3 nodes, one is the node reference and 1, 2 are non-reference node. So, node voltage V1, V2 are assigned and also the direction of branch current are marked to reference applying the KCL to node 1 and 2. So, that is typically I1 equal to I2 plus I3 at node 1 here. So, at node 2 typically you have a I2 plus I4 and typically I2 plus D2 current are entering, other 2 are leaving, that is I1 plus I5. So, applying Ohm's law at KCL equation, so Ohm's law says I1 equal to I2 plus I3, that is a 9 equal to V1 minus V2 upon 6 or plus V1 minus 0 upon 0. So, that becomes 3 V1 minus V2 equal to 54 and the Ohm's law at node 2, that is I2 plus I4 equal to I1 plus I5. So, it is V1 minus V2 by 6 plus 6 and that is a current source and plus equal to 9 plus V2 minus 0 by 1. So, you get another relation V1 minus 7 V2 equal to 18 and solving these equation we get the V1 equal to 20.077 and V2 equal to 6.2307 volt like. So, there are some unsolved problems, I mean you can just solve to get the voltage between these two terminal by making the mesh analysis and similarly this also here you can have a loop equations and get the value of voltage. So, there are some these you can solve in the similar manner these solved problems like based on that. These are the some references and thank you.